Good morning, everybody. As a preliminary to this talk, I define a short function called bits, which when given an integer prints it out in a 32-bit binary notation. You'll see why that is useful to my talk as we go along. This is the Mighty Dictionary, and we're at PyCon 2010. How do you think, if you've never looked under the cover, can Python lists access every one of their items with equal speed? Whether you look at the first or the 7,000th item in a list, it tends to come back in a fairly constant time. The answer is that because Python lists use segments, contiguous chunks of RAM in your computer, and it just so happens that RAM acts precisely like a Python list. It's a big array addressed by sequential integers. It is even zero-based, just like the list you're used to. So it was very easy for the Python people to implement lists atop RAM. A dictionary's problem, of course, is that the keys can be any kind of value that you can come up with, and yet they still have to somehow efficiently find the objects you've stored in RAM. So the problem of the dictionary is how can we turn keys, which can be anything, into indexes that need to be sequential integers? Well, they came up with 3 rules. For those of you who are computer science savvy, I'm about to describe the implementation of a hash table. First, a dictionary is really a list. When you start out with an empty dictionary, it actually behind the scenes is creating an 8-element list or table in a contiguous block of RAM. I might occasionally call this a list and items to continue the analogy with lists, but the correct term that I'll often use is a hash table, and I'll call the entries in its slots. The second rule is that keys need to be hashed to produce indexes. What's a hash? Well, Python actually exposes its hashing function to you. This is something nice about a language like Python, that it supports introspection and lets you see its internals. A hash is a mathematical algorithm that gets a string like Monty or a number like pi or a tuple and reduces it to 32 bits of ones and zeros. And it does it in such a way that it kind of scatters the information in the original piece of data all across the ones and zeros. Monty and money only differ by a single letter, but you can see that their hash values, I put little chevrons under the bits that differ, that single few bits of difference in that one letter gets scattered across the entire hash. So a hash is a big binary number that's very different for even slightly different values, and when you run hash on a value, you always get back the same number. This is going to be important when we go back to a dictionary an hour later and want to find a key again. So, in order to build the indexes that it needs to get into the list, into the hash table, Python uses the bottom n bits of the hash. So let's say that we start with this empty dictionary and we want to store something under the key FTP. Well, it's going to compute the hash, it's a big binary number, pull off the last 3 bits, 001, and go check that slot, find that it's empty, and decide to store the key and value there. When you want to store SSH's port number, it hashes SSH, looks at the last 3 bits, oh, that slot's free, SSH goes there. SMTP, the big long hash, ends with 100, and that's a free slot. Time ends with 111, and www happens to end with 010. And at this point, we have a 5-element dictionary stored in RAM where we can get very quickly back to any of the values in it, because lookup just does the same 3 steps. When you come back 20 minutes later with a key, it just computes the hash, truncates it down to 3 bits, and looks in that slot and finds it. You want to print D of SMTP, it can jump right there. Even though the dictionary has 8 slots in it, it immediately jumps to the right one. One consequence you can already see of this up at the level of the Python you use is that dictionaries tend to return their contents in a crazy order, You go through and we just put all of those things in order by port number, but when you print out the dictionary, it just comes out in some crazy order. It turns out it's not a crazy order. If you look, it's printing out the dictionary in the same order as its items are stored in the hash table. Even though it looks like a crazy order from up at our level, it's just starting at the first element of the hash table and reading down the list. That's why you can grab the keys of a dictionary, the values of a dictionary, and zip them together and knowing they'll correspond. Every iteration over a dictionary is simply a visit in order to each slot in the table, reading off the ones that don't happen to be empty. And this is where things get complicated and where the story gets interesting and worthy of a full talk. The third rule, and last, is that if at first you don't succeed, try and try again, because it was just good fortune that the last 3 bits of the hashes of those keys that I just tried happened to not be the same. I mean, you know, there's only 8 possibilities, so very often 2 keys you try will have the same 3 lower bits in their hash. That's called a collision, when 2 keys in a dictionary want the same slot. Let's start over with a fresh dictionary. A first item, SMTP, reaches an empty slot and inserts fine. I'm now going to store appropriately enough, the port number of the dict internet service, and it hashes the string dict to a hash that ends in 100. And oh no, that's already used. I'm not going to go into the mathematics that Python uses here, but it uses a recurrent function that uses those so far unused upper bits in the hash that we haven't been using to create a list of secondary backup locations in the dictionary that, for storing this particular key. So for the word dict, that math and the upper bits of its hash happen to choose the slot 001. It's free. So dict is now not in the place it wanted. It is 1 step away from where it wanted to go. SVN at 000 goes right in. Our dictionary now has 3 items. But if we now want to store IRCD's port number, that string has 000 at the end of its hash, and that's occupied. That backup algorithm happens to choose, in that case, 001 is the next backup, that's taken. 100 is the next slot, that's taken. So IRCD winds up landing 4 slots away from where it started, all the way down in 110. If we now, just for fun, add the port number of ZOP in last, it wants to occupy, again, 000, try 001, and because its upper bits are a bit different, its third try is different than IRCD's was. That's why it's so good to use those upper bits to throw a little randomness into that search for a backup location. So it winds up in 011 rather than going down the same path that IRCD did. So it gets in on only the 3rd step, only the 3rd place that it tries. Well, we've now created a little dictionary, 5 elements in it, the size of the one before, but only 2/3 of the keys in this dictionary are found in the right slot. Fully 3/5 of them collided and have wound up somewhere else and are thus a little deeper in the dictionary, and it's more expensive to find them. So let's start drawing some consequences. First, because collisions move keys away from their natural hash values into a backup location, key order is quite sensitive to dictionary history. If we build, for instance, the dictionary in the order in this order, which is the order by port number, it happens, they go in the order we just found, and SVN happens to be listed first if we ask for the keys. What if we build the exact same dictionary, though, and insert IRCD first? Well, it then gets to grab slot 000, and it's SVN that has to go hunting for a backup location when it comes its turn to be inserted. This means that even though those 2 dictionaries I just created, D and E, are from Python's point of view identical, Python is going to tell you that semantically those dictionaries mean the same value. Nevertheless, their keys are going to come out in a different order. They've both arrived at the same value, but because they've taken different routes to having that set of 5 keys, the order is different, and that's why you can't rely on dictionary ordering. Another consequence we can immediately draw is that our lookup algorithm is going to be more complicated than just hash, truncate, and look, because we're essentially, until we find an empty slot, when we go looking especially for a key that's not there, we're going to have to keep bouncing around till we finally reach an empty slot, because for all we know, the key is out at the end of some big list of collisions. So for instance, getting the dictionary we created a moment ago and looking at SVN, the end of its hash is 000, and SVN is indeed the key at that location, we can return its value immediately. If we look up IRCD, when we find that it's not at location 000, we can't immediately raise a key error. We have to start jumping down its path to 001, 100, and 110 before we can decide whether it's really in the dictionary or not. So lookups become more expensive as well as inserts when a dictionary begins to experience collisions. If we do an unsuccessful lookup that immediately happens to hit a blank slot, like for NSCA, which hashes to 101, we can immediately raise a key error. But if you go in looking for netstat, for the netstat service, it's going to try 100, 001, 000 before finally hitting the blank slot 101 and being able to conclude, no, nobody has ever inserted this key into this dictionary. So, as a consequence of that, not all lookups are created equal. Some are going to be expensive and some are going to be immediate, depending on whether they hit a bunch of full slots before concluding whether their key is present. So here's a stupid dictionary trick number 1 that you can try at home. It happens that when I began the presentation and showed you hash values and showed you how pretty they were with 1s and 0s all through them, I didn't show you the hashes of any integers, and that's because Python does something special. For integers, rather than try to come up with some crazy way to spread their bits across a 32-bit word, they instead decided that each integer is its own hash. The hash of 1 is 1. The hash of 2 is 0000010, and so forth. This means that if we want to do annoying things to dictionaries, we can just use integers and thus dictate exactly what their hash value will be. So here I've created a dictionary which is all collisions. I'm using 3 and then 3 plus multiples of 8 so that the lower bits of every single one of these integers is 0, 1, 1. So it inserts 3, 11, 19, and you can see that even though I'm trying to pound in on the dictionary and put everything in the same place, the fact that it pulls in the upper bits to decide the path from there does pretty well. You can see that they're spreading themselves out among a number of locations, but by the time you get to that last element, it's a 4-level, it's having to hit 4 different slots before it can be stored. And if we now use timeit to look up how expensive is it to look up D of 3 versus D of 35, you can see that in fact there is a slight but measurable difference that you can see from the command line between something that's lightly collided and something that's at the back of several dictionary collisions. Consequence number 5 we can now draw is when deleting a key, Python needs to leave dummy keys in its place. So think about this. Let's say that I get tired of having SMTP stored in this dictionary and I want to delete it. Can I simply mark its slot as empty again? Well, think about this. What happens when we look up IRCD? Do you remember? It tries to go to 000, then 001, and 100 before finally finding it in the fourth, or the third backup location, the 4th place it looks. If we were to mark the SMTP row as empty and blank, then the search for IRCD would terminate there, and we would lose the key and value that are stored way off in location 110. So when a key is deleted, its slot can't simply be marked as empty. Otherwise, any keys that collided with it and got sent off elsewhere would be lost because searches would terminate immediately upon reaching the slot. So we create something called a dummy key instead. All it does is eat up space in the dictionary. It can be reused for storing a fresh key, but until some new key comes in to use slot 100, there's got to be something there for collision searches to continue to bounce off of to make it to their destinations. So we have deleted that key, but we can still find IRCD because the search will bounce off of that and keep looking. That leads to a possible stupid dictionary trick number 2 that you can try at home. You can create a dictionary of keys, go through and delete most of them, but leave a badly collided key as distant from the beginning of its search as it was when you created the dictionary. Here I have a dictionary that, because of its history, having 5 elements created and then 4 of them deleted, I've managed to create a dictionary with 1 element that collides 3 times on its way to being discovered. So you can actually create sparse dictionaries that, merely because of their history, have very expensive keys to look up. So at that point, the story just gets better from here. Because dicts refuse to get full. You cannot fill that table I just showed you with 8 entries. Because collisions are expensive, dicks resize when they get to 2/3 full. Small dicks go ahead and chew up 4 times the memory. They quadruple the size of that table. When they get kind of big, they start doubling so they don't waste too much of your RAM with empty slots. So let's watch a dictionary in action. I'm going to grab some words from the dictionary on my Ubuntu box. Start with an empty dictionary. Put in the first 5 keys. It happens that the words in the dictionary, 2 of them collide, so we're up to a collision rate of 40%, but that's as big as it will let this get when we pass from 5 to, by adding the word abash, 6 keys. Python goes ahead and reallocates the dictionary now as a 32-element hash table, and the collision rate suddenly drops to 0. How can it do that? Because, let's go back, these only collided because we were only considering the last 3 bits. But you'll notice in gray there, the bits right above those are different. We could distinguish these keys and put them different places if only we could use more of the hash bits. And indeed, you can see that's what happens when we expand up to 32 elements, because you need 5 bits to distinguish among 32 possibilities. We're now using enough of the hashes that, in this case, they happen to be completely distinct. By the time you get up to the 21st word that you insert, you're 2/3 full again. The collision rate has gotten about as bad as it will at 29%, and the dictionary now feels too full again and resizes to 128. There's only 2 collisions once it's now considering, I believe, all 7, the lower 7 bits in each hash. So the collision rate is, there's only 2 words in there that collide. When you're up to 85 words, you're now 2/3 full again. Collision rate up about to 33%, and the slide would just get too crowded if I showed you the next resizing, but that cycle continues on and on. So the life cycle as a dictionary fills, is it gets more crowded as keys are added, then suddenly less crowded again as the dict decides it's too full and resizes. So, consequence number 6 that we can draw and observe, average dictionary performance is excellent. Let's grab another group of words. Here I started with the capital words in that file. And let's examine which keys collide. There's a little library I've written called dictinfo, which will be released with the source code to this talk. Yes, this is a doc test, and I ran it to make sure it was correct. Called dictinfo, which lets you ask for a key in a dictionary what series of probes are being done as it hunts in that hash table for where this key is. So we can ask for these capital letter words, the first few hundred that I've put into a dictionary. Let's go back one slide. I created a dictionary of size 1,365 words because that's right at the verge of the dictionary being too full and resizing. So we're looking at a pretty crowded dictionary. Some words like Ajax and Agamemnon are found immediately because they're right at the slot you would expect them. Aristarchus, as an example, requires 5 probes to find, and it just so happens that the word Baal is 16 collisions deep in this dictionary. It's, I think, the only word that is, but it has to hit 16 different places every time you look it up before it finds the slot that it's stored in. So, on the bottom here is the size of the dictionary as I store more and more and more words in it. The red line is kind of what Baal is doing, what the few keys are doing that are just getting clobbered because they're behind so many other collisions. And sure enough, you can see it jumps up to 16 when Baal gets added and is put all the way at the back of a long collision. But now turn your attention from the worst case, which does seem to increase to more than a dozen and then drop back as the dictionary resizes, and look at the average case. The average case never even manages to reach the number 2. That is, for every Baal that's 16 deep, there's like 20 keys which are being found immediately. So despite those few keys that behave badly, the average isn't even being pushed to an average of 2 slots having to be searched for an average key in the dictionary. Then the story is even better than that, because probes are very, very fast. I know I've been making this process of finding a collision and finding another collision. I've been making that sound really tedious and expensive, but in machine terms, Python doesn't even, in most cases, bother comparing the values of the keys. It just compares the hashes. Because two equal keys will have equal hashes, and you can usually throw out the possibility of their being equal immediately just by comparing those 32-bit values and not even have to look at the two strings or integers or whatever to see if they match. So on machine terms, this search is just comparing two 30-bit numbers, doing a compare, doing a quick bit of math to find the next place to look, and you're off and running looking at the next location it could be. So the difference between looking up Ajax, which you'll remember was 1 probe deep, and Baal that was 16, is only a factor in time of 1.7 once you include all of the overhead of making a get item lookup and a function call in Python in the first place. So here's the same graph as before, but showing the number of nanoseconds that the lookup requires on my laptop rather than just the question of how many collisions occur. And you can see that even though Baal is 16 probes deep, it doesn't even manage to double the cost of looking something up that's found immediately. The keys that are found immediately take 60-something nanoseconds. The very worst don't even reach 120 nanoseconds. So the best and worst behaved keys in a typical dictionary have less than a factor of 2 in the time that it takes to look them up. Look at the average performance. It would be lost in the noise of your processor in most calls to time it. It's a tiny difference in the cost on average of looking for a key because collisions exist. We can now draw a seventh observable consequence. Because dictionaries resize aggressively, a dictionary can completely reorder during an otherwise innocent insert. You can have a dictionary whose keys are coming out in an order you've kind of gotten used to, and if you happen to add a key that throws it over that 2/3 threshold, so it's now using higher level bits to choose a completely different order for the keys, the dictionary will just come out in a completely different order. Consequence number 8, of course, is that because an insert can radically reorder a dictionary, key insertion is prohibited during iteration, a rule you already know, but you now understand that it could completely change the internals of the dictionary, so it can't occur while an iterator is active across it. So what do I hope you take away from this talk? Well, first, for those of you who didn't know the math and the technique here of how a hash table works, if you go to university and take a course on data structures, they geek out about this kind of thing the whole semester. But I hope that those of you who just use the dictionary but didn't know how it works will now have a mental model that makes sense of those arbitrary rules you were having to follow. You didn't know why you couldn't rely on the order or insert while you were iterating over it. And I hope now that instead of those just seeming like senseless rules, they now make a little sense and maybe you'll be able to remember them better. Second, this is a big computer science theme. Dictionaries are a perfect example of trading space for time. They always are wasting a lot of your memory by keeping empty slots around. I mean, right after a resize, less than half of the dictionary is being used for active storage of keys. You saw how empty and vacant the dictionaries looked in my pictures right after a resize. They're spending a lot of space, using a lot of space, but they're buying you time as a result. Because they choose to place things sparsely in memory, they can get to them quickly without a lot of expense. And in all kinds of places in computer science and in your own programming, you'll find this difference between being able to cache things and use memory, but get time in return. That's why in Python, if you need more space, and you can't have 1,000 of these dictionaries in memory or 1,000,000 of them, there are other alternatives, both for data structures you can use that are more efficient in their storage, and if you want to turn off the fact that your classes use dictionaries in the back end, you can of course give them a slots variable to disable that, because it is an expense and you should be able to avoid it. Finally, if you're writing your own class and you want to store its elements, you want to store instances of your class in a dictionary, you know you need to write a hash function. You might not have understood how it's going to be used. You now know that it is the magic quantity which is going to help your items land at different spots in the dictionary and not all pile in the same place. Scatter bits like crazy. Remember that if 2 of your instances evaluate equal, they've got to have equal hashes or they won't find each other in the dictionary again. Remember, you've got to also implement an EQ method, because once Python sees that the hashes match, the next step in the lookup is to compare the keys to make sure it's not a pair of keys that just happen to have the same hash but are themselves different. And hash and equality have to be quick. If your hash function is expensive, or if it's very expensive for you to compare equal, you're not going to be a very fun object to use as a dictionary key. Very often you can just get away with getting whatever Python variables you're storing, whatever your instance variables are, and just XOR them together, exclusive OR them together. Let Python worry about how to build a hash and just combine the hashes that Python's already willing to generate for the values that you're holding. Equal values always need equal hashes because the hashes are checked first before the keys are checked for equality. And look at what Python did. So that a naive user can store something in a dictionary under the integer 9 and then come and look it up with a float 9.0 later, it was long ago decreed that all values that represent an integer should return the same hash as the integer itself will. And that's a neat bit of flexibility they built in. This is the end of my talk. May your hashes be unique, your hash tables never full, and may your keys rarely collide. Thank you very much.
If anyone has a question. I have. Can you please come use my phone?
Jump over the desk.
We're talking about how the hashes will resize to a larger state as it becomes needed. Does the reverse also apply? As it becomes sparse, do they resize back down?
Resizes are only calculated upon insertion. As a dictionary shrinks, it just gains a lot of dummy entries, and as you refill it, it will just start reusing those to store keys. It will not resize until you manage to make it 2/3 full again at its larger size. So it does not resize as you delete keys. You have to do an insert to get it to figure out it needs to shrink.
Is there a way of forcing it to resize so that it comes back down?
Not that I know of. You'd have to copy the keys and values
Because
into
as
a
it
new
gets
dictionary.
larger and larger,
Agreed.
you're trading space for time, but now you're just trading space
For
more
space.
space and more space and more space.
If you copy the
and
keys
you don't get
and
the time, you don't get the time.
if you copy the keys and values and do a new dictionary, you get to start over.
So just do a copy.
Yeah.
Okay.
Yes, sir.
Are there any differences between the characteristics of the set container? Like, does it work the same way as far as colliding keys and resizing?
I don't know. I would have to go look, but we can go look during the break or something. The question was whether the dictionary stored things the same way as the, which one? Set. Oh. Yes, I'm sorry. A set is a dictionary without storage for the value.
What about true hash collisions where you have two keys that really do evaluate to the same hash even though they're not equal? How does it map out the lookups?
If two keys have the same hash through all of the bits, they will follow the exact same series of collision points. So one will get the first slot in that sequence and the next one will get the second slot. And then when you go to look up either key, Python will not only compare the hashes because they'll come out equal, it will have to take the ultimate step of then comparing the keys for equality and say, oh, look, this string I'm looking for matches the hash, but it's not equal to this key. I'd better head on to the next slot and keep looking. Yes, sir.
Is there a way to predefine the size of a dictionary? If you know you're going to create a dictionary with 100,000 entries, is there a way to create that rather than just having to do all the inserts?
I think that there's a way to do that at the C level if you're calling the C function for creating a dictionary. Does anyone know if that's exposed up at the Python level? I'm not aware that it is. So if it is, I don't know how.
Thank you.
Yes, sir.
Is it true that every time the hash table is resized, it forces the keys to reorder?
If a set of keys, so in general, yes, But you could contrive an example where that wasn't the case by choosing 6 keys that had the same 4th and 5th bits. You would insert them into your little 8-element dictionary, and when it resized, because those 4th and 5th bits that are now brought into play by the 32 slot table were the same, you'd find you would get a little miniature version of your earlier dictionary in the section of the table that started with those 2 bits.
And just as a follow-up, is it an expensive operation to do the reordering?
It's like copying the dictionary to a new dictionary. It takes a few moments. It's a malloc of new memory, and it has to go through and do a new reinsert on every entry. I didn't have time to make a graph of the time, but the little spike that the reordering, in the little expense of the reordering, on average costs nothing. It just makes those particular moments expensive. But there are so many moments you then get, so many inserts that are free, because the dictionary is already now big enough for them, that on average it's not time you need to worry about. Thank you.